Hey guys, welcome back. Got an easy one for you today. So today we're going to be looking at the converse of the Pythagorean theorem, which is actually a way that we can use what we know about the lengths of the sides of a triangle to determine what the shape of the triangle is, classifying it by its angles. So let's look at classifying triangles and see what we remember about that. So there's different types of ways we can classify triangles by their sides. So if all three of them have the same length, then we know that it has to be an equilateral triangle, which means that all the lateral sides are the same. We also call this equiangular, right? Or equilateral, same thing, right? If two sides are the same, then we know their base angles have to be congruent, which would tell us that this is an isosceles triangle, which means two angles are the same and two sides are the same as well. Then, but what do we have if all the sides are different, right? So if all three sides are different, then we know all the angles have to be different as well. But then what kind of a triangle is it? We just call it scalene, but is it a right triangle? Is it acute? Is it obtuse? It really could be any of them. I mean, if it's equilateral, it has to be acute, right? Because they all have to be 60 degrees. You could have an isosceles obtuse triangle. Yeah, that's possible. You can have an isosceles right triangle or an isosceles acute like this one. So we don't really know. So classifying the sides, we need to know the lengths, specifically the lengths of the sides, in order to be able to determine whether or not it's acute, right, or obtuse. So one thing that I do want to show with the triangle inequality theorem is that we realize the smallest angle is going to be opposite of the shortest side. The medium angle is opposite of the medium length side, and the largest angle is going to be opposite of the longest side. So we can put them in order from smallest to greatest, and then the lengths of their sides, also their opposite sides, are going to be in the order of smallest to greatest as well. So the opposite side is opposite, the smallest side is opposite the smallest angle. All right, so what we need to know is which one is opposite of the largest angle. So if it's a right triangle, meaning if the largest angle is a right angle in this case, then we know that the a squared plus the b squared is equal to c squared. If you remember the last video there, I showed you the animation, showed you the visual proof, the mic drop. It was pretty awesome. Hope you guys enjoyed that. And some other applications like if I ever coach football, which will never happen, right? Can you imagine me coaching football? Not gonna happen. Anyway, but I'd probably do it with a compass, and it'd be really nerdy if I set up defenses like that. But hey, whatever. Anyway, we learned that if it's a right triangle, then a squared plus b squared is equal to the c squared. So we can use that actually by looking at the converse of that. So the converse, remember, is like shoes on the wrong feet. We're just going to switch the order. So that tells us that if the a squared plus the b squared is equal to c squared, meaning the sum of the two small sides squared together is going to be equal to the largest side squared, then that means that it must be a right triangle, right? So then it must be a right triangle. So that statement is actually true. So if it's a right triangle, we know the Pythagorean theorem holds. And then if the Pythagorean theorem is true, then we know that it has to be a right triangle. So in fact, the true Pythagorean theorem is the conditional statement. If it's a right triangle, then a squared plus b squared is c squared. So then the converse of that statement would be true as well. So if a squared plus b squared is equal to c squared, then that means that the side, that the angle that's opposite the longest side has to be a right angle. So what happens when it's not a right angle? Well, then it's either going to be acute, obtuse, or equiangular, and we'll figure out how to be able to determine those lengths as well. So we could also classify angles, triangles as acute if their largest angle is less than 90. If the largest angle, which was the one opposite the longest side, is bigger than 90, then it's an obtuse triangle. If it's equal to 90, then it's a right triangle. And if they're all the same, if they're all 60 degrees, in other words, then it would be equiangular. So the converse of the Pythagorean theorem tells us that if the a squared plus the b squared is equal to the c squared, then it must be a right triangle. So let's determine if this is a right triangle. We have two sides of 6, 6, and then 9. So this is isosceles. We know that because two sides are the same. So that means these base angles are the same. But that still doesn't tell us about the angle that's opposite the longest side. The angle opposite the longest side has to be our largest angle. That's the one we really need to know about. Is it 90 degrees? Is it less than 90 degrees or more? Let's find out. So let's plug it into the Pythagorean theorem. I'm going to do this where A is the smallest side, B is the next smallest side, and C is the longest side. So that's just how I'm going to do it. The two smaller sides, again, the order on those two wouldn't actually matter, but just just for consistency, I'm going to do it from smallest to greatest. So in this case, the two smaller sides are 6. So we have 6 squared plus 6 squared is some relationship to the c squared. Now, we don't know if they're equal or not. That's what we're going to try to find out. Our longest side in this case would be 9. So that would have to be our hypotenuse if it is hypotenuse. So whenever I put that in the calculator, you can put it straight in there if you want. You're probably doing this on your phone. So we'll do 6 squared plus 6 squared. And that's going to give me 72. Also, you can do it one at a time if you need to. So you could do 6 squared, which is 36, and then plus another 36 will give you 72. Anyway, and then the other one we have is 9 squared, which is 81. So I have 72 and 81. Now, I noticed those are not equal to each other, so I know this cannot be a right triangle by the converse of the Pythagorean theorem. So what kind of a triangle is it? Well, I don't know. At this point, all I know is it's not a right triangle. So there's really two other options we could have. We could have where the a squared plus b squared is greater than a c squared, or if it's less than the c squared. And that would mean that it would have to be either acute or an obtuse triangle, right? So let's try to figure out the best way to remember which one of those it would be. So let's look at the example of the equilateral triangle. This is actually how I remember the cases of which one's which. Now, on an equilateral triangle, all the sides are going to be exactly the same, which is going to make our formula kind of really easy to work with. And all the angles also have to be the same as well. So all these angles are all going to be 60 degrees, right? So that's 60, this is 60 degrees, and this is 60 degrees here as well. So this is this is definitely acute, right? There we go. I can't spell apparently. Acute. All right. So the largest side, which I don't know which one's the largest, they're all the largest, right? Is going to be opposite the largest angle, which is 60 degrees. So this is definitely acute. All right, well, when we plug it in for all three sides, and again, they're all the same length, so it doesn't matter. We're going to have a squared plus a squared is equal to a squared. So I'm just going to let the side length be a in this case. Well, a squared plus a squared is 2a squared, which is twice as big as 1a squared. So when the a squared plus the b squared is bigger than the c squared, like in this case, it's twice as big, then what kind of a triangle is this? Well, this was always an acute triangle. So whenever we have the a squared plus the b squared is bigger than the c squared, it's an acute triangle. So if we look back on our previous example, we had 72 was not equal to, it's actually less than the c squared. So what kind of a triangle would this have to be? Well, if these two were bigger, I guess I'll write here, if they were bigger than the c squared, then that would mean that this is acute, right? Okay, so if it's actually truly less than the c squared, then the only other thing it could be would be obtuse, right? And sure enough, this would be an obtuse triangle if we graphed it out. All right, so what kind of a triangle is this one? Well, we got sides 5, 6, and 7. So I'm going to plug it in here with the Pythagorean theorem's converse and check it out, see what we get. So 5, 6, and 7. So 5 squared plus 6 squared is some relationship to the 7 squared. Well, that's 25 plus 36. Again, you can put it all in the calculator if you want, but that's going to be 61. And then 7 squared is 49. All right, so this is going to be greater than the c squared. So again, if you remember when the a squared plus the b squared is bigger than the c squared, just like in the example of the equilateral triangle, like 2a squared is bigger than 1a squared, then this has to be an acute triangle. And sure enough, it would be an acute triangle. All right, so if the a squared plus the b squared is equal to the c squared, then it must be a right triangle. And this is basically from the Pythagorean theorem, converse of Pythagorean. Then we saw if the a squared plus b squared was bigger than the c squared, then it must be acute. And the example we remember for that one is the equilateral example. So the a squared plus the a squared is 2a squared. It's twice as big as the 1a squared because it's got a really small, the other a is really small in this case, which would mean the obtuse side, or the longest side, the hypotenuse, is not long enough to make it where it's bigger than the a squared plus the b squared add together. So what happens when the c is so long, the longest side is so much bigger than the a and the b, that even when we square the a and the b and we add them together, they're still going to be less than the c squared? Well, that, of course, has to be when this is an obtuse triangle. All right, so what kind of triangle has these sides? Well, the only thing I can do to make this any harder, because really it's not that bad, is add radicals to it. But when we square a radical, it's just going to go away anyway, so it's not that bad. So first thing is we might actually want to approximate this. So I know this is going to be approximately 7. I think it's about 7.1 or something like that, because the square root of 49 is 7, so it's just going to be a little bit more than 7. All right, so we have 3, roughly 7.1, and then 8. So I'm going to put them in order as 3 squared plus rad 51 squared is some relationship to 8 squared. Well, the 8 squared is 64. When I square the square root, they go away, right? because the 1/2 power of a square is just going to be 1. So that's going to be 51, which is pretty simple. They just kind of cancel each other out, right? So 51 plus 9, which is 3 squared, would give us 60. All right, so we got 60 plus 64, or sorry, how is 60 related to 64? Well, they're not equal, so it's not a right triangle. So is it acute or is it obtuse? Well, it's less than this, meaning the C was so big that it was bigger than the A squared to the B, then it's going to have to be an obtuse triangle. It's a good way to remember that one. All right, so let's get started on the assignment. Really simple, easy stuff. We're going pretty fast today. We have 3, 8, and 10. We want to decide, is this a triangle, first of all? And then if it is a triangle, what kind of a triangle it is? So I'm not sure where I was supposed to... I forgot to tell you about that. But the other thing we have to do is make sure that it actually forms a triangle. So in order for it to form a triangle, the two small sides have to add up to be larger than the longest side. So if I'm drawing this triangle here, so on the bottom we have 10, and then I have a side length of 3, and then a side length of 8. So this side we'll say is 3. That was terrible. And this side over here we'll say is 8. Where those two intersect, this point right here has to be our actual triangle. So we have a side length here of 8, and on the other side we have a side length here of 3. It's obviously not to scale, but you get the idea. So 8 and 3. Now, in order for these to meet, they have to add up to be larger than the longest side here. So 3 plus 8 is equal to 11, and 11, sure enough, is bigger than 10. So they will make a triangle, but just barely. So if they were any smaller, like if this was 2 and 8, then it would not actually make a triangle because they're not quite long enough. So if you remember, we've talked about that a little bit before. All right, so it is a triangle. The only question is what kind of a triangle. So let's do the Pythagorean converse. We're going to do 3 squared plus 8 squared is some relationship 10 squared. So just put them in order from smallest to greatest. 10 squared is 100, right? And you can put that in the calculator. I'm just going to put it in the calculator just so you can see how I do it. So that's going to be 3 squared plus 8 squared. So basically 64 plus 9 is 73. And 73 is not equal to 100, so it's not a right triangle. So our only options are acute or obtuse, because it is actually going to make a triangle. It's big enough. So in this case, if the C is so big that the C squared is bigger than even the A squared and B squared together, then it's going to have a really long side, which is going to make it obtuse. All right, so it is obtuse, and you can cross it off on your answer bank. Number 10, we got a radical here, but when we square a radical, it just goes away, so it's not that big of a deal. This is going to be close to 10, because it is square root of 100 is 10, so it's going to be just a little bit more than 10. So 12 plus 10 is 22, which is definitely bigger than 15, so it does make a triangle. The only question is what kind of a triangle. So I'm going to put them in order. So we got rad 108 squared plus 12 squared and then 15 squared. Remember, the radical and the square root, they undo each other because it's like the 1/2 power of a square. So we have 108 plus 12 squared, which is 144. I can just put that all in the calculator if I want. So 108 plus 12 squared. I want to do 11. I want to do 12. All right, so plus 12 squared, which is going to give me 252. And then this is 225 if I put it in the calculator. So now the A squared plus B squared is bigger than a C squared. And if you remember, that's very similar to the equilateral where we had A, and A, which was where 2A squared was bigger than the 1A squared, which had to be an acute triangle, right? So in this case, if the A squared plus B squared is bigger than the C squared, then that means that this has to be acute. And sure enough, this is an acute triangle. Number 11, we have 11, 11, and 22. So first we want to check, does it even make a triangle? Well, if we have side lengths of 11, 11, it is isosceles, it's true. But where are they going to intersect? Well, 11 and 11, if we add them together, that's equal to 22. So they will intersect, but they're going to intersect on the line right here, where this side is 11 and this side is 11 as well. And so they're not going to be long enough to make a triangle. They would have to be bigger than the 22. The sum of the two small sides has to be bigger than the longest side in order for it to be able to make a triangle. So since these two are equal to 22 and not bigger than 22, this is not going to make a triangle. Kind of cool. All right, number 13. Now this is one normally we would actually construct in class with compasses, and it's a lot of fun, but because we don't have compasses, I just went ahead and constructed them for you, and I even measured them for you as well. All right, so on this one, this is using Thales' theorem, I believe, one of his many theorems. This is probably the cooler one, but anyway, Thales' theorem here says that the third side of any right triangle is going to be anywhere on a semicircle, where the other two vertices of the right triangle are on the endpoints of the diameter. So these must be right triangles. This is a way that we can create any possible right triangle length that has this diameter here. And you'll actually see this again with the equation of a circle, which we'll be doing in our next unit right after spring break. So that'll be kind of fun. So we have lengths here of 6.8 and 14.1, and then another length of 12 and 10. And then the diameter on the bottom should be about 15.6 centimeters. So we want to check to make sure that these are actually right triangles by using the converse of the Pythagorean theorem. So putting it in the calculator, what is 6.8 squared plus the 14.1 squared? And that's going to give me 253.6. Okay, and apparently I did something wrong. Let me double check that. So 6.8 and 14.1. Try that again. All right, there we go. That's better. And then we want to do the hypotenuse squared, which is 15.6 squared. And we're going to check. Now, these are not going to be exactly the same, but they're really, really close. They're approximately equal to each other. There is limitations in the precision that we have. Like this one could be closer to like 14 and a half centimeters or 14.08 centimeters. But our closest, the most precise we have is actually going to be a millimeter. So it's actually, that's pretty impressive. So we're good to go. This is a right triangle. It's just our limitations were how precise we could measure. So you can check the other one, do the same method. So 12 squared plus 10 squared, take the square root of that, and it should be really, really close to the 243.36 as well. All right, so then on the back side, again, we would have compasses so we can actually graph these out, and you can see the Pythagorean theorem in all of its glory and its converse in real life. So here we have lengths of 7, 7, and 4.5, just like we did side, 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 congruency postulate, right? So if we have all three sides here, we can figure out, obviously, well, both of our longer sides are 7, so this one has to be an acute triangle, right? Because you can't have two obtuse angles in a triangle because they're limited. They have to add up to 180. So anyway, let's put it together with the Pythagorean theorem. So we have 4.5 squared plus 7 squared, and is some relationship to the 7 squared. Well, the 7 squared is 49. Then to do the other side, I'm going to do 4.5 squared plus the 7 squared, which will give us 69.25. Now that's clearly going to be larger than this one. So just like the example where we had 2a squared was bigger than the 1a squared, this has to be an acute triangle. So our logic by the converse of the Pythagorean says this has to be an acute triangle. And when we construct it, sure enough, it is going to be acute. And this is actually like drawn to scale. If we look at our largest angle, which both of these are kind of the largest angles in some way or another. Oops, let me fix that. That looks better. Okay, that was a little bit off, but you get the idea. Let me delete that out of the way. So it's 72 degrees, which is going to be less than 90 degrees. So now let's look at number 18. This is one of my favorite problems. I really, really like this problem. I first came across it with my when I was working with some test prep with my cousin, and really challenging problem, and it's amazing the elegant solution that comes across. It's just a beautiful problem. All right, so in the problem, we have a cylinder that is 12 feet tall and has a circumference, which is the distance around it, of 8 feet. Then they say that there's a string that wraps, or a rope that wraps twice around and spirals around this cylinder. So it starts at the bottom and ends at the top of our cylinder. Then the question simply asks, what is the length of that string? Well, at first thought you might think, well, the circumference is 8 feet around and it's going around twice, then the length of the string has to be 16 feet, right? But it's not just going around the base of the cylinder, it's also going up the cylinder. So it's going up 12 feet, right? So then it would be, what, 16 feet plus the 12 feet that it goes up. So altogether, what would that give me? 28 feet. But it's not 28 feet either. It's going to be something different. So kind of a weird thing going on here. The best way to think about it is actually to model it out. So here we have our three-dimensional barrel, and then over here we have the two-dimensional net, which will actually be really important. So if we start out on the bottom and we start tracing the line here. It's going to go all the way here, and it's going to go back around. That'll be one complete rotation, and it's gone halfway up the barrel, right? Then it's going to go another way, then along the back here, and it's going to end right on above the same spot that it started, because it went 2 full rotations and it went up 12 feet. Okay, so if we look at this, how in the world do we find the length of a spiral? I mean, it's like a spring or something. That sounds really complicated. But if we convert it, instead of a 3-dimensional cylinder here, if we change it to a 2-dimensional net, which would just be like a rectangle, imagine cutting this barrel along this blue line and then unfolding it and laying it out with the string still around the outside. So what would that look like? Well, this point here is going to go all the way across until it gets to the very end, which is going to be the same as this point over here. Those are going to be exactly the same point. So cutting it from here, it's going to go across. It's going to look something along the lines of this. So here's our first half of the barrel, and if I wrap that back around, it would go this point, the blue point, is the same as this blue point all the way over here. They're going to match up right above the original red point there. Okay, cool. So then let's do another, the last rotation is going to do the same thing just on the top part here. So this is what it would look like if we undid it. So you see the first half on the front, then the back half, first half on the second half on the front, and then the second half on the back part. So you can see the colors and how that lines up. Now remember, the length of this is going to be the circumference, right? So that's going to be the 8 feet going around, and then the height that it's going to travel altogether is going to be 12 feet. Now, if we're going to break this down into 2 parts, half of that 12 feet would be 6 feet here, and then we got another 6 feet here. So let me duplicate that just so you can kind of see how I broke that down. All right, so then the next question is, we don't want this 8 feet plus a 6 feet. That's what we did originally, the 16 plus a 12, which is 28. Because we're not traveling these lengths here. We're actually traveling this diagonal length. Now, if we look, this is actually a right triangle. And then we have the length of this is actually the hypotenuse. So that's like our C, and this is like our A, and this is our B. So if you haven't guessed, how are we going to solve for the length of C? Oh, we'll use the Pythagorean theorem, right? So let's put this in our calculator and see what we get. So let's do 6 squared. So 6 squared plus 8 squared, which is going to give us 100. And then the square root of 100 is 10. All right, so that means that C, in this case, must be equal to 10 feet. Kind of cool. So C squared was 100, so that was equal to 10 feet. Let me go ahead and clear out all of the ink. There we go, so it's out of our way. All right, so if this length here for the first spiral is going to be 10 feet, then we know the same thing is going to happen on the other one, right? Because it's going to be the exact same 8 and 6 feet. So the total length of our rope or our string is going to be 20 feet, and that is the correct solution. Something that seems really complicated whenever you're dealing with it in 3 dimensions, but once we break it down to a 2-dimensional net, all of a sudden it's not quite so complicated. And something as measuring the spiraling length of a string, whenever we roll it out flat, just becomes 2 right triangles in the Pythagorean theorem. So what a beautiful application of the Pythagorean theorem. I hope you enjoyed that. I was working with my cousin, who I think at the time was 11 years old. So totally capable, I mean, obviously for you guys to grasp this, but just a beautiful application of the Pythagorean theorem, popping up in an unexpected way. So hope you enjoyed that. Let me know if you have any questions. Pretty easy day. I just spent a lot of time, I guess, on the last problem here, so sorry about that. Then after this, we're going to move into special right triangles, which are going to be 2 challenging topics. So make sure that you got the Pythagorean theorem and reducing radicals and stuff down really well, because we're going to need those radicals, especially multiplying them, for our next 2 lessons that we're going to do. So I'll see you guys back in class eventually, whenever all this snow and stuff is over. So I'll see you guys around. Let me know if you have any questions.